Hello everyone. Today I wanted to talk a little bit about the Rogers-Ramanujan Continued Fraction. So, let's get started. Well, first of all, what is a continued fraction? It is one of the types shown on the screen where the expression may or may not terminate. And if it does not terminate, we call it an infinite continued fraction. So just like we can have infinite series as well as finite sums, we can have infinite continued fractions as well as continued fractions or normal fractions. We want to know when an expression of this type converges and what it means for an infinite continued fraction to converge is that the sequence of truncated continued fractions converges to a well-defined limit. There are many very beautiful examples of infinite continued fractions. For example, the ones shown on the screen are particularly delightful for pi and e, and these are not particularly difficult to prove, even though they are very delightful. And the simplest infinite continued fraction is the one where the numerators and denominators are all ones. And that's the continued fraction for 1 over the golden ratio. And the natural generalization of this simplest infinite continued fraction is when we replace the q's, the ones in the numerators, by powers of q. And well, perhaps the q to the 1/5 is not very natural, and indeed it is not necessary to include it. Only sometimes when we include it, it helps make certain relationships which are of q satisfies. It makes certain symmetries in these relationships more apparent, but it was not necessary to include it. So the Rogers-Ramanujan continued fraction, which we denote by R of q, converges when q is in the open unit disk. And this is perhaps the most beautiful continued fraction in mathematics for many reasons, but one of the reasons is because it has particularly delightful explicit evaluations. For example, the one shown on the screen is the first non-trivial one found by Ramanujan, of course. The theorems which Ramanujan had about the Rogers-Ramanujan continued fraction serve to give Hardy a very high opinion of him when he sent him letters, as everyone knows. And among his theorems was included the explicit evaluation shown on the screen. And Hardy was very impressed by these theorems and said that they must be written down by a mathematician only of the very highest class. And indeed, Ramanujan was of the very highest class. So our goal today is to give a brief outline of how one can prove this particular evaluation on the screen. So like, what are the tools that we need in our toolbox which would enable us to give a proof of this? So first of all, before getting into the matter, let me just note that this result is believable, because if you just truncate the continued fraction to the term e to the minus 4 pi, then it converges very fast, because even then, to 10 decimal places, the result agrees with what is claimed. There is a point also that I would like to make, is that In mathematics, usually when you interchange between any two of infinite series, infinite products, and infinite continued fractions, if you know how to do it, then usually you will get a beautiful result. The most famous example of this is perhaps Euler's resolution of the Basel problem when he equated the Taylor series expansion for the sine function with its Hadamard product. And the Rogers-Ramanujan continued fraction can be converted into infinite series and infinite product as shown on the screen. So actually in the quotient of infinite series, the numerator is actually equal to the reciprocal of the infinite product in the denominator, and similarly for the infinite series in the denominator, it's equal to the reciprocal of the infinite product in the numerator. And these two equalities are known as the Rogers-Ramanujan identities. And there's a vast amount of literature on this and many generalizations, many different proofs, and interesting combinatorial interpretations. And I would encourage you to learn more about this. But about these conversions here, these are fundamental results which are used to prove many beautiful theorems about the Rogers-Ramanujan continued fraction. We won't have time to prove them in this video, but we are outlining a proof of the explicit evaluation we saw before, and we need these. Okay. And it turns out that in order to have a fruitful study of the Rogers-Ramanujan continued fraction, a particular class of functions is very useful. These are the theta functions. I have not defined all the theta functions on the screen for every complex number z and every tau in the upper half plane. I have only defined one theta function. Here q is equal to e to the pi I2. And perhaps the most important result in the theory of theta functions is the Jacobi triple product identity, which gives a product representation for the theta functions. And there is, if you have heard of Euler's pentagonal number theorem, it's actually a particular case of the Jacobi triple product identity. And actually the Jacobi triple product identity encloses surprisingly a lot of information. For example, you can just manipulate it algebraically and differentiate here and there. And you can deduce theorems like Fermat's 2 squares theorem and Lagrange's 4 squares theorem. There is also another result in the theory of theta functions whose importance cannot be overstated, and it's the theta function transformation. As innocent looking as it might seem, this theta function transformation is actually quite deep. For example, Riemann, in his paper of 1859, where he stated the Riemann hypothesis, he made use of the theta function transformation in order to give an elegant proof of the functional equation for the Riemann zeta function. And you can also prove things like quadratic reciprocity using the theta function transformation. Okay, so these were two very fundamental and important results in the theory of theta functions. And one of the most important formulas for R of Q, which is the Rogers-Ramanujan continued fraction, is the one shown on the screen. And you can prove this using the Jacobi triple product identity. By the way, if we had not included that q to the 1/5 in the definition of R of q, the left side here would be not quite as symmetrical in the corresponding formula. And it turns out that if you put q equals e to the minus 2 pi, then you can actually give a closed form for the resulting infinite product on the right if you use the Jacobi triple product identity and the theta function transformation. And this gives you a very nice equation, and this should be very exciting because if we denote R of e to the minus 2 pi by x, we can rewrite the last relationship like this, and this can easily be turned into a quadratic equation which everyone knows how to solve. And when you solve it, you get x equals this delightful closed form, which is exactly the explicit evaluation which we wanted to outline the proof of at the beginning. And there are actually, of course, many more results that exist around the Rogers-Ramanujan Continued Fraction. For example, if we made use of the things that have been shown in this presentation, with only a little more work, we could have proved the following two results. So the first one is a very closely related closed form evaluation for the Rogers-Ramanujan Continued Fraction. And the second one relates R of q to R of q to the 5, and that is called a modular equation of degree 5. And actually these two results on the screen were both in Ramanujan's first letter to Hardy. And now you can't just use a single method to prove all that there is to prove about the Rogers-Ramanujan continued fraction. For example, you would need to do more work if you wanted to prove these two results on the screen. The theorem below is particularly delightful because it tells you that you can get two closed form evaluations for R if you know only one. And these also were known to, Ramanujan stated them. Of course, he didn't leave proofs, but no doubt he had them, because how can you just come up with these things without having some sort of proof? And finally, I would like to share with you certain resources if you would like to study more about the Rogers-Ramanujan continued fraction. Well, first of all, there is so much about the Rogers-Ramanujan continued fraction, and perhaps the source which contains the most information about it is Ramanujan's lost notebook, of course, but the edition of it by Andrews and Bent. It's called Ramanujan's lost notebook, although it was neither a notebook nor was it lost. But anyway, this book contains a very great number of results on the Rogers-Ramanujan continued fraction and more explicit evaluations. If you want a gentle introduction to R of Q, then you can read chapter 7 of Number Theory in the Spirit of Ramanujan, also by Bent. This book is very delightful and contains a lot of succinct and elegant proofs. And finally, if you would like to study theta functions, a very good introduction would be chapter 21 in Whittaker and Watson's A Modern Course of Analysis. People often joke about the word modern in this title, but anyway. Well, okay, that was what I had to say for today, and thank you very much.